Alright, this is probably my third take of trying to do this, but essentially what I'm going to do is show you a few videos on YouTube. I'm going to link to these because I'm filming a screen of a screen right now. So you probably want to get maybe a better view of these on your own computer itself. But basically, I've got a few videos here of transverse and longitudinal waves. First one we're going to do is transverse wave. Basically, what this person has is they have a slinky and it's hooked up to just something that's fixed here, and you can shake it up and down. What they're doing is they're doing this with their hand, and what that does is that generates pulses. And here's, you see the single pulse here is traveling from right to left. And what you also want to notice is that the medium itself, it moves up and down while the pulse travels right to left. That's what happens in a transverse wave, and that's what we saw in that FET simulation that I might bring in a little bit into this video. Next one that we want to talk about is a longitudinal wave. It's going to be a little bit different because he's going to take, and the slinky is going to create a disturbance by doing this, pushing that way, and then back out again. And if you pay attention to that, what you're going to see is you're going to see this compressed region move from right to left. It travels through the medium, and you can see it going. When it hits the end, you may notice a little bit of reflection as well. And one other thing I'll probably show you here is this guy's demo of a longitudinal wave. He does a continuous,
and if you could imagine,
he does a continuous wave by doing it back and forth consistently. So if you take a look at the medium here, you're going to see it moves pretty fast, but the medium itself, you have several successive vibrations in the left and right direction. And what you really want to pay attention to here is that the medium itself in this particular wave is traveling in the same direction as the wave. The disturbance is in the same direction as it. It's parallel to it as opposed to perpendicular. All right, so basically what we did was we focused on the transverse wave for this little app here, and that's what a transverse wave does. But we'll go to the pulse one. A single pulse. When you focus on any individual particle in this medium here, you're not going to see the particles move from left to right. What you're going to see is you're going to see the medium moving up and down. So this is your transverse wave. Your motion is perpendicular. Excuse me, the motion of the medium is perpendicular to the motion of the wave. The medium goes up and down. The wave goes left and right. There's a 90-degree angle between the two. When you do a continuous pulse, it looks like this. And what you see is that this is very sinusoidal in nature. But look at the medium again. Just look at a single particle. If you focus on a single particle, it always moves up and down. It cannot move right and left. The only thing that is moving to the right now is the wave. So you got to be able to distinguish the wave motion from the motion of your medium itself. The next thing I want to probably show you is a longitudinal wave. And basically, one of the examples of a longitudinal wave is a sound wave. So when you have speakers do this. They push out and they pull back in, and what they do is they basically shape the air around it. If you take a look, this is what the particles would look like for a longitudinal wave. Now what I really want you to focus on here is that you can clearly see that the waves are moving to the right here. This kind of looks like a helicopter view of waves in an ocean. But if you focus on one individual particle, any one, you're going to notice that they rock back and forth. They don't continuously move to the right. So you can pick any dot there and focus on it, and you're going to see that dot moves back and forth and back and forth and back and forth. So again, we have to distinguish between the disturbance and the wave motion itself. All right, so the wave motion is clearly exclusively to the right, but the disturbance is back and forth and back and forth. All right, so those two things we definitely want to make note of here. Just write out our definitions really quickly. All of these things are examples of what we call mechanical waves. That's what we're focusing on in this chapter now, is mechanical waves. These are waves that require a medium. That could be a linear medium. It could be a nonlinear medium. but it has some sort of physical medium here. So what am I talking about? String, like the app. Spring, like the slinky. We could do water. For the sound, it was air particles. All right, you don't have to be able to see the medium. All these things are physical mediums. And basically, the other type of wave that we're not going to look at right now would be waves that don't require a medium. An example of that's like light. Light doesn't need a medium to travel through. For example, the sun's light can travel from the sun through space to us, no problem at all. All right, now we have two types of waves that we're going to focus on in terms of the mechanical waves. We've got our transverse waves. So, motion of the wave is perpendicular to the disturbance. And then you have longitudinal. Motion of the wave is parallel to the disturbance. All right, so pretty easy to understand once you've seen the videos. Again, I'll link them just so that you can see those videos a little bit more clearly. And let's hit stop here and go on to a different video.